Okay, molecular orbital theory, electron delocalization. So what we talked about yesterday with the valence bond theory is an improvement on Lewis theory. And yet it still doesn't explain everything, and we can do better. And molecular orbital theory is the higher level of understanding bonding. The idea here is that we can look at quantum mechanics and we can see that atoms have orbitals, and we studied those. And those are, for students, those are a bit challenging, but they're doable, right? But then when we bring atoms together to form a molecule, Lewis theory assumes that everything is the same. And in valence bond theory, we recognize, okay, these orbitals are not quite working out. Maybe we need to hybridize them, and so that helps. But the thing is, in a molecule, the orbitals are different than the orbitals in an atom, and so hence the name molecular orbitals. These are the orbitals found in a molecule. And these come from the Schrödinger equation, but it's impossible to solve exactly. This is one of those, hairy math things that we're not going to go into. So you can't actually solve the Schrödinger equation exactly, even for a simple molecule. And so what they do then is they do more of an iteration method where you propose a trial function. You say, okay, well, here's a good guess, and then we'll see how that fits, and we'll go from there. The analogy in your book is it's a little bit like solving, something like this. 12x plus 17 equals 59. And how do you figure out what x is? Well, that's a simple equation. You could solve for x. But without solving for it, what you would do is you'd say, well, maybe x is 5. And you'd plug it in and see how it works out. And then you would adjust x from there, either up or down. It's an approximation. And so that's what we do with these molecular orbitals. So of course, we're not chunking these out by hand with a calculator. We use computers to do this, powerful computers, and they crank through all these numbers. And so they calculate the energy of the trial function, and then the trial function is adjusted, optimized, to get the lowest energy. Because it's always going to be the lowest energy function that's going to be true. We can never do better than nature at minimizing the energy of the orbital. No matter how long you spend calculating molecular orbitals for molecule, you're never going to find one that's lower than the actual orbitals in the molecule. So one way to look at these molecular orbitals in a more simplistic way than actually solving all these functions and minimizing energy is using a weighted linear sum. So LCO stands for linear combination of atomic orbitals. So this is taking two atomic orbitals and bringing them together, but it's not just a simple average or a simple addition. It's a weighted linear sum. So we bring these two orbitals together. This is the simplest trial function that actually works reasonably well. And so these combine the valence atomic orbitals of all the atoms in a molecule. And in molecular orbitals, we're talking about electrons being delocalized over the entire molecule and not being localized between two atoms. What valence bond theory does with its hybrid orbitals is it only combines orbitals from a single atom. So we talked about hybridizing carbon to sp3. We were looking at the atomic orbitals that carbon as an atom had. Molecular orbitals, now we're taking orbitals from carbon and orbitals from oxygen and combining those into new orbitals, because that's what actually happens when a molecule forms. Many of these LCAOs, linear combinations of atomic orbitals, are delocalized over the entire molecule, whereas the hybrid orbitals remain localized on a single atom.
I'm not quite sure about that last one, delocalized.
Okay, so we drew pictures yesterday showing the lobes of these orbitals and how they overlapped. And those were drawn between, here I'll draw one of them. You know, say we have something very simple. Here's a hydrogen with its s orbital, and it's overlapping with maybe a p orbital from carbon. And this is between these two atoms, and the rest of the molecules over here, and all of the electrons are between two particular atoms, and the orbitals are localized. When in fact, for many molecules, these electrons are actually shared throughout the entire molecule. They're delocalized, and so they can be in different places. They're not, the simple thing when we talk about, you know, a covalent bond, two electrons shared between two atoms, and there's the attraction between the negative electrons and the positive nuclei, and that's what holds it together. And that's just a very simplistic approach, which is a great place to start. But this would be a localized situation, and these molecular orbitals, the orbital is over the entire molecule many times. Any other questions? So let's look at hydrogen, H2. So here's one hydrogen atom. It has a 1s orbital, and here's another hydrogen atom with a 1s orbital. And when we make molecular orbitals, if we combine these two atomic orbitals, we're going to end up with two molecular orbitals. So we're just looking at the first one right now. One way to combine these will end up with a shape like this. This is called a sigma orbital because of its shape. It's cylindrical if you look down the bond axis. And it's 1s because it is from 1s or atomic orbitals that are being combined. This is a bonding electron, a bonding orbital, because the energy of it is lower than the individual energies of the atomic orbitals. So you take these two 1s orbitals, you bring them together and combine them, and one result of that is a bonding orbital that's lower in energy. But when you combine two orbitals, you get two orbitals. So one is the bonding orbital. The other one arises from combining this 1s orbital with the negative or the opposite phase. Remember we talked about phases and how when we look at a wave, it has phases, the peak and the trough, and they have phases, and when they interact, they can reinforce constructive interference and destructive interference. And all of the atomic orbitals, because they are wave functions, they have phases as well. It's a little hard to see on the s orbitals because you can only see one phase at a time. It's not like the p orbitals where one side is one and one is the other. But if we take this and combine it with the opposite phase of this one, basically we're subtracting them in a way. We end up with something that looks like this. Like, how do you get that? Well, it's not easy to understand how you would get that, but that's what we get. It's complicated. But this has a node in the middle, and one side has a positive phase, and one side has a negative phase. This orbital, this molecular orbital, is higher in energy than the atomic orbitals it started with. So the first orbital was constructive interference of the two orbitals, and this is like destructive interference because of the opposite phases. So where they're overlapping, they're canceling each other out, and there's nothing there. This is called an anti-bonding orbital because it has a higher energy. And so this is indicated by sigma 1s because it is it's a sigma shape orbital, but it's 1s because it's formed from 1s, and then to indicate that it's the anti-bonding orbital, we put an asterisk there. So when we combine these two, when we add them, we get something that's lower in energy, and when we subtract them, we get something that's higher in energy.
This is all happening at the same time?
Yeah. Exactly, right? This is a challenging topic, but just try to stay with me here. So here again, we have these two pictures. With destructive interference between these two waves, we get something that looks like this. And with constructive interference, we get something that looks like this. And if you look at this, it looks like that is going to hold those two atoms together, doesn't it? Because we have a lot of electron density here in between. And this has a node right between these two atoms. That's not going to facilitate holding the atoms together in a bond, if that helps you to remember that this is an anti-bonding. So we have this node, this region of 0 electron density between the nuclei, where with the bonding one we have high electron density. This is lower in energy, that's a good thing. This is higher in energy, that's not a good thing for bonding. So we make diagrams, and those were pictures of shapes and stuff, but we make diagrams. These are related to orbital diagrams that we did when we first learned about quantum mechanics. They're called molecular orbital diagrams. And this helps us to see how the different orbitals are combining into the molecular orbitals and what their relative energies are. So here we've got the atomic orbital diagram for hydrogen. It has 1 electron in the 1s orbital, and here's the other hydrogen atom, 1 electron in the 1s orbital. And those 1s orbitals have the same energy as each other. When we combine these, we get 2 orbitals. We get a bonding orbital that's lower in energy and an antibonding that's higher. So this is sigma star 1s and this is sigma 1s. The star means it's an antibonding orbital. So here, 1 electron from this hydrogen atom, 1 electron from this hydrogen atom, and they're going to fill up these molecular orbitals. They're going to fill the lower energy one first. So in an H2 molecule, we have 2 electrons in this bonding orbital, and that forms the hydrogen bond. Yes?
So these would be bonding since they both form the hydrogen bond?
Right. The combination of these is a bonding and an antibonding. And then when you go to put the electrons in, they're going to go into the ones with lower energy first. And so in this instance, we see, well, this is probably going to be a stable molecule because we have electrons occupying the bonding orbital and the anti-bonding orbital, which is working against us, is empty. And we'll go into that in a few minutes, more details about that. Any other questions? Yes?
So both the orbitals do exist right now, just one is empty?
Right. The orbitals exist whether they are filled or not. Just like in a hydrogen atom. You can elevate or excite the electron from its ground state in the 1s orbital up to a 2s orbital or something, and that's where we get the absorption of light and the emission of light when it comes back down. So all those places, those orbitals, those regions of probability are there, whether they are occupied or not. Very good point. Any other questions? So we talk about a bond order. The bond order for a diatomic molecule is the number of electrons in bonding molecular orbitals minus the number in antibonding divided by 2. So for hydrogen, let's go back and look at that orbital diagram. Here's the bonding orbital. There are 2 electrons in there. The anti-bonding orbital is empty. So we take the number of electrons in bonding orbitals, subtract the number in antibonding orbitals. So that gives us 2. And then we divide by 2, and we get 1. So this is a bond, that one has a bond order of 1. If the bond order is positive, we can predict that the bond will form because the electrons are going to have lower energy than they would in the individual atoms. And the higher the bond order, the stronger the bond. If the bond order is 0 or negative, it will not form. how could you get a 0 bond order? Let's go back to this guy. If we had a different element here and we had 2 electrons in the antibonding orbital, then our bond order would be 2 in the bonding orbital minus 2 in the antibonding orbital over 2, and that would be equal to 0. There's no advantage for those atoms to bond together because the average energy of these guys is going to be the same as in the individual atoms. There's no lowering of energy, so there's no benefit in creating a bond. So the bond order helps us to recognize or predict if the bond actually forms or not. So the more electrons you have in bonding orbitals, the stronger the bond, and the more you have in the non-bonding or anti-bonding orbitals, the weaker it becomes. And that kind of makes sense. So let's look at helium. So an He2 molecule. Well, here's the orbital diagram for helium. It has 2 electrons in the 1s orbital. And over here we have another helium atom. These 1s orbitals are going to combine in the same way to form a sigma bonding orbital and a sigma antibonding orbital. Antibonding with higher energy, bonding with lower energy. And then we have 2 electrons here and 2 electrons here, and we're going to put them in, filling them up in the same way that we filled up orbital diagrams before. You fill the lowest energy ones first. So we'll put 2 in here and 2 in there. Well, what's the bond order then? Well, this is 2 minus 2 divided by 2. It's a bond order of 0. Is a bond going to form between 2 helium atoms? No. And from what we learned about the noble gases, do you think He2 exists? No, it doesn't. What about an He2 plus ion? Well, it being an ion means that it's lost 1 electron. So one of these has 1 electron and the other has 2. That would give the combined ion a +1 charge. So here again are those antibonding and bonding orbitals. Now we have 3 electrons, so we'd put 1, 2 in here, and the third one would go up there. That changes the bond order. So we have 2 in the bonding orbital and 1 in the antibonding, and we divide that by 2, and we get a bond order of 1/2. It's positive. So that the bond order predicts that He2 plus ion exists, and in fact it does. It's not something we use a lot in general chemistry, but it does exist. Any questions?
The bonding and anti-bonding, because 1 electron from the He atom and then 1 electron from the ion go together, or just...
That's a good question. Just asking, is it these 2 electrons that are down here and this one up there, or is this one from here and one from there? And I think the answer is it doesn't really matter. Yeah, we're just looking at total number of electrons. It's a good question, though. Anybody else? So, summarizing, we can approximate molecular orbitals as linear combinations of the atomic orbitals. And just like when we were hybridizing orbitals, the number of molecular orbitals that are formed is equal to the number of atomic orbitals. So if you start with 5 orbitals and you're combining them into molecular orbitals, you end up with 5 orbitals. You don't gain or lose orbitals. When 2 atomic orbitals combine, you get 1 bonding and 1 antibonding. The bonding orbital is lower in energy, and the antibonding is higher in energy. When you assign electrons, we do the same pattern we did before. You fill the lowest energy orbitals first with up to 2 spin-paired electrons. And Hund's rule is still going to apply. if you have molecular orbitals of the same energy, they're going to fill singly first with parallel spins, up arrows, and then they will pair up as needed. In order for it to be a stable bond, the bond order must be positive, which means that you have more electrons in the bonding orbitals than in the antibonding orbitals. So that's a summary of what we've talked about so far. Let's look at an example. Use molecular orbital theory to predict the bond order in He2+. Is the He2+ bond stronger or weaker than the H2 bond? Okay, so what we're going to do, remember energy is going up that way. And we're going to start with our atomic orbitals. So this is 1s, and this is 1s. This is 1 hydrogen, and this is 1 hydrogen. So if we just have hydrogen atoms, they would each have 1 electron. And then when these combine, when the atomic orbitals combine, we're going to get 2 molecular orbitals. One is lower in energy, one is higher in energy. This is the sigma star 1s, and this is the sigma 1s. And then oftentimes we draw these little dashed lines to show that those orbitals came from these two. So that would be H2 we would be looking at. But if it's H2 plus, do we add an electron to this or subtract one? Subtract one. So we need to get rid of one of these. So you could do the right one or the left one. It doesn't really matter. Let's just erase that guy. And then this is H plus. He has no electron. So when these combine, we have 1 electron. It's going to go into the bonding orbital. And then what's the bond order? It's going to be 1/2. Because we have 1 in the bonding orbital and none in the antibonding, and then we divide that by 2, and that's equal to 1/2. Any questions?
So that means it exists.
Yeah. The fact that the bond order is 1/2 means that this ion does exist. Now, is this bond stronger or weaker than the H2 bond? It's weaker. Because the H2 bond, there was a second electron in here, right? For H2, we had these guys, and this is gone. And then the bond order is 2 minus 0 over 2, which equals 1. More positive bond order, stronger bond. Questions? So that was period 1, hydrogen and helium. Let's look at period 2. Homonuclear diatomic molecules. The prefix homo means the same. Homonuclear, the same nucleus. Diatomic, 2 atoms. So this is a molecule made of 2 atoms of the same element. We're gonna stay with the small and simple things. So the next set of molecular orbitals is going to be a linear combination of the valence atomic orbitals in the period 2 elements. So we're looking at valence orbitals still. So for lithium, lithium has the 1s2 as its core electrons. The core electrons are not involved in bonding. It's the valence electrons. So lithium's valence electron is in the 2s orbital. So here's 1 lithium atom, here's the other lithium atom. When we combine these 2s orbitals, again we get a bonding and an antibonding orbital. Now this is sigma star 2s, and this is sigma 2s, because this is the linear combination of the 2s orbitals. One higher energy, one lower energy. This lithium atom has an electron. This one has an electron. We take those two electrons, and they're going to fill up the bonding orbital. So the bond order for that, then, is the same as for H2. We've got 2 in the bonding, minus 0 in the non-bonding, and divide by 2, and that's equal to 1. So Li2 has a bond order of 1. That suggests that it does exist, and it does in the gas phase. Any questions?
Does the bond order number that you get tell you what phase it exists in?
No. The bond order that you get tells you nothing about the phase or anything like that. It just predicts that this would be a stable bond. This is, Li2 is not lithium's normal state. H2 is hydrogen's normal state. Hydrogen is generally found as H2. Lithium is usually found, if it's an element, as a solid with metallic bonds, just lithium. But when you put it in the gas state, then it does form Li2. And so some of these things, I think what probably happened is they're looking at this and, oh, well, this is predicted to exist. Let's try to find it, right? Let's see if we can isolate it and prove that it exists, or prove that it doesn't exist. Any other questions? So let's look at the next element, beryllium. Again, with the 2s orbitals, but now those 2s orbitals are full. The 2s orbitals combine to form a bonding and an antibonding orbital. Now we have 4 electrons, and so we'll get 2 in the bonding and 2 in the antibonding. This has a bond order of 0. It's predicted to be unstable, and that is true. It is not stable. We look at this, and energy-wise, there's no reason for 2 beryllium atoms to bond together. There's no energy reason for them to do that. Could you force them to do it? Yeah, probably, but then they're gonna let go. It's like making 2 children hold hands. You know, you were fighting, now make up and hold hands. And as soon as you turn your head, they're gonna let go, aren't they? There's no incentive for them to hold hands. Next one up is boron. Well, boron has an electron in a p orbital. So now we have to look at the p orbitals. The p orbitals are going to be combined pairwise. So there's direction here. So if we're looking at these orbitals, what we've decided is that the internuclear axis, the line between the axes, between the nucleus, I'm sorry, let's start that over. The line between the 2 nuclei in this molecule, we're going to call that X. And then Y and Z on the axes are perpendicular. So if we look at combining the 2px orbital for each of these, p orbitals have positive phase in one lobe and negative in the other. And when you put these 2 together this way with constructive interference, you get a big lobe in the middle and little lobes on the end. And when you subtract them, essentially flipping this one, then the middle part kind of cancels out and you get big lobes on the outside. This will be higher in energy, and this one is lower in energy. My stylus is messing up. These are also called sigma bonds. The stylus is not on the there we go. All I have to do is talk about you and then you shape up. These are called sigma bonds. There we go. These are called sigma bonds again because they're cylindrically symmetrical. If you look down the axis, so that you could see from one nucleus to the next, if you're looking down that axis, they're symmetrical, they're spherical. Looking from the side, they're not spherical, but looking from the end, they are. And so that's why it's called a sigma bond, it's spherical. The other two are going to be added side to side. So here, if we call this coming in and out of the plane of the screen, Y, then when we combine these, in phase, we're going to get these, we'll get two lobes, but they'll be between the nuclei. And when we combine them out of phase, we get four lobes and this big node in the middle. This is the anti-bonding orbital, and this is the bonding orbital. The Z direction, the vertical, is going to do the same thing. So when you combine p orbitals, there's 3 p orbitals. And you combine 3 from each atom. That's a total of 6 orbitals you're combining. You're going to end up with 6 molecular orbitals. There's the Z. And so when they combine in phase, constructive interference, we get these lobes here. And these are holding these nuclei together, and this would be pushing them apart. So we have bonding and anti-bonding. It's not just neutral, it's against bonding. Yes?
What do the little round blue circles mean?
These little circles, those are the nuclei. So here's the nucleus, and here's the nucleus. And so these orbitals now are not like, right on the nucleus, but they are above and below and holding together, as opposed to these where there's nothing in between. This is higher energy, this is lower energy. Questions?
Why is it that the anti-bonding, it's not really a bond, but it's a higher energy?
Well, higher energy is bad. It's like, stuff rolling down a hill. These atoms coming together, they're going to share if sharing gives them lower energy. If it causes an increase in energy, they're not going to want to do that. If you want to think of energy as money, it's like, well, I'll share a hotel room with you if we get a deal, right? If that's going to save us money. But if it's going to cost me the same, I'd rather have my own space. Okay? So if there's an energy savings, if the energy is lowered, the bond will form. If the energy goes up, it will not form. And if it's flat at 0, it's not going to form either. Not going to stay. Any other questions? So when we put these orbitals together, the relative energy ordering for these 2p combinations is not the same for all molecules. So that's kind of a bummer. For boron, carbon, and nitrogen, the order is different than for oxygen, fluorine, and neon. How do we know this? This was determined computationally. Big old powerful computer, putting in functions and doing all that hard math. So the typical energy ordering is this, that the sigma 2p and the pi 2p are lower in energy, and then the sigma star, the anti-bonding, is next, and the sigma star is the highest energy. So let's look at that. So for boron, carbon, and nitrogen, when we combine the 2s orbitals, we're going to get the sigma 2s and the sigma star 2s. And when we combine the 2p orbitals, we're going to get, remember, we can get a sigma bond from the p orbitals, the ones that are in the x-axis and aligned end to end. So that's the sigma 2p. The pi 2p's are actually lower in energy, and the antibonding pi 2p's are lower in energy than the antibonding sigma 2p.
That's not always the case, right? How do we know when it isn't?
How do you know when it isn't? You remember, be careful now. Boron, carbon, nitrogen. So this is the order for boron, carbon, and nitrogen, and this is the order for the other things. So what's the difference? The difference is up here. Here we have the sigma is the lowest energy for the bonding and the highest for the antibonding, and the pi, the pi orbitals are in the middle. Okay, and this is what, at least to me, makes a lot more sense. This is more what I would expect to happen. This is not expected. And so what this is offset. These guys are lower, this guy's lower and that guy's higher. The order of these two is switched. So this is what I would like you to learn as an expected order. And then be careful now, if you're doing boron, carbon, or nitrogen, you have to flip these. This one and this one are switched.
So that's only for like the diatomic molecule.
This is only homonuclear diatomic molecules, yes. That's limited, isn't it? Yeah. This method, this theory describes things really well, but it's very complicated. And so we're going to stick with very simple molecules. We're just kind of getting our feet wet. And then if you go on in chemistry, you'll study molecular orbitals more. But even among PhD chemists, there's only ones in certain areas of study that really care that much about molecular orbitals. And they care a great deal about them, but, you know, this is not something fundamental to chemistry that you have to understand to be a chemist. We have to know about it. Doing molar masses, doing stoichiometry and gas laws, that stuff's really important. Any other questions? So these slides are posted on Blackboard, and actually all these figures are coming out of your book, so you also have them in your book. And if you want a copy, you can go to Blackboard and print them out from the PowerPoint slides. So here is another way of comparing the order for these two. Here's, be careful now, boron, carbon, nitrogen. The sigma 2s is lowest, and then the sigma star 2s, and then the pi 2p. Wait a minute. Yeah, I guess they're leaving out the antibonding orbitals for the p. And so they're showing us that the pi 2p orbitals, the bonding orbitals, have the same energy, and that the sigma 2p is higher for, be careful now, and lower for the OFNE. I'm not entirely convinced of the usefulness of this. That might help. I think what they're trying to show us is that these are different because of this increasing 2s, 2px mixing, and these have less 2s, 2p mixing. It is what it is. As bond order increases, the bond gets stronger and shorter. So here are the molecular orbital diagrams for these 6 different elements. And notice that the ordering of these orbitals is different for boron, carbon, nitrogen than it is for these guys. So for boron, we've got 6 electrons, 3 from each boron atom. These are the valence electrons. They're going to fill up the 2s bonding and antibonding orbitals, and then the pi 2p bonding orbital will have 2 electrons in it. So this one is going to have a bond order of 1. Carbon is going to fill up the pi 2p bonding orbital. It's going to have a bond order of 2. Nitrogen has a bond order of 3. So now we're getting in here. And none of these antibonding 2p orbitals have any electrons in them. That's why this is increasing. And if we look at the bond energy and the bond length, this confirms that this bond order business does have some predictive quality or value. So bond order of 1, the bond energy is 290 kilojoules per mole. Higher bond order, 946, higher bond energy. The bond energy is the amount of energy that's released when the bond is formed. And the amount of energy you would have to put in to break the bond. We also see that the bond length gets shorter. A stronger bond is shorter. So this is 110 picometers, this is 159. When we jump over to these guys that have the more expected order, what flips here is that this 2p bonding orbital is now up here, and the sigma, so let's just make a note of what's changed here. So these have switched like that. Okay, that's what changes. So now, oh, I didn't mean to do that. We've got the pi, this is the bonding orbital, is full here. Now we've got 2 electrons in the antibonding orbital. So this bond order is only 2. And as we continue to add electrons into these antibonding orbitals, the bond order decreases. And when we get to neon, we see the bond order is 0, which predicts that neon does not form a diatomic molecule, and that's true, it does not. Any questions? I forgot all about this link. Let's watch it. So we know from experiment that oxygen is paramagnetic. Remember, paramagnetic has some unpaired electrons and is attracted to a magnetic field. Diamagnetic, the prefix dia means 2, and we decided to remember that that meant that everything was in 2s and they were all paired up. Paramagnetism, direct result of unpaired electrons. If we look at the Lewis model and the valence bond model, oxygen has no unpaired electrons. And so neither of those models explain why oxygen is paramagnetic. Here is the valence bond concept of an oxygen molecule, where we have sigma bond here, and we have a pi bond here, and then we've got these electrons in lone pairs in the p orbitals, and there's no unpaired electrons. So let's draw a molecular orbital energy diagram and determine the bond energy, the bond order for the N2 plus ion. Did I miss something? No, I didn't. Seems like there should be something else there. Do we expect the bond to be stronger or weaker than the N2 molecule, and is N2 plus diamagnetic or paramagnetic? You know what I'd like to do first is draw the diagram for oxygen. Because we were talking about oxygen and somehow just left oxygen there, and that doesn't seem right. So let's look at oxygen. Okay, so valence electrons for oxygen. What are they? We've got the 2s. Oh, I should probably leave a little more space. And the 2p, right? And it has 6 valence electrons. So there's going to be 1, 2, 3, 4, 5, 6. So that's one oxygen atom. And then over here is going to be the other one. And that's going to have the same electrons in it. 2p and 2s. You with me so far? Bless you. So then we need to combine these. Let's see if I can remember. These are hard to remember, these orders. So the S stays down by itself. And so we can just do these over here. The s orbitals will make a sigma star 2s and a sigma, I don't know what that was, 2s and a sigma 2s. So those guys are going like that. Oh, good grief. I'm just having no end of trouble with this. And then these pi, the pi orbitals, remember, one p orbitals, one p orbital from each will overlap end to end in a sigma bond. And that's going to be the lowest. So this is sigma 2p. And then we're going to have 2 that are pi 2p. Oh, I made this way too small. And then next up will be the anti-bonding pi star 2p. And up here will be the sigma star 2p. So these guys, it's not my best work here by any stretch of the imagination. What a mess. Just to make you guys feel better about your scribblings. So how do you learn how to do this? Well, we need to, for the S's, it's not as hard. We got 2 orbitals combining. We're going to get one that's higher, one that's lower, anti-bonding and bonding. With the p orbitals, and I didn't draw these out very well, you're going to get 1 sigma and 2 pi's for bonding and for anti-bonding. This is the regular order. And be careful now, boron, carbon, nitrogen, those are the ones that do it a little funky. So we got our molecular orbitals in the middle. Now we're going to take our electrons and we're going to fill them in. So we've got 6 from here and 6 from there. That's a total of 12. And so we're just going to put them in. 1, nope, zoomed in too far. Start at the bottom. 1, 2, 3, 4, 5, 6, 7, 8. They'll go in singly there first. 9, 10, then they'll pair up. 11, 12. 12 electrons. Looking at the molecular orbital diagram, is oxygen paramagnetic or diamagnetic? It's paramagnetic. It has 2 unpaired electrons. Those other theories didn't account for that. They didn't explain that. molecular orbital theory does. What's the bond order for oxygen? Well, let's do it. Okay, bonding. This is bonding. There's 4, 6, 7, 8. Right, so that's 8 bonding and 4 non-bonding, anti-bonding, right? Am I counting right? Divided by 2, so 8 minus 4 is 4 divided by 2 is 2. Bond order of 2, predicting that O2 exists. Questions? I'm moving kind of slow here because this is new to most of you. Yes?
Why didn't you fill the top one? Like, what order did you go in?
Okay, that's a good question. Why didn't I fill this top one? Well, the height here represents the energy. So as we go up in our diagram, energy is increasing. And they're going to fill the lowest energy ones first. So here there's only one, it's going to have a pair of electrons. Here there's one, it gets a pair, this gets a pair. Here there are 2 at the same level, and so we'll put 1 here and 1 there, and then it has to pair up. And then we go up here, 1 in each. They don't want to go up to this more expensive level unless they have to. You go to the hotel, you know, and you're a cheapskate, and you're going to take the cheap room. It's like, yeah, but the penthouse is available, and it's got this blah, blah, blah. And it's like, no, I can't afford that. I want the cheap room. You're only going to go up there if you have to. Okay? Good question. Other questions?
How do we get 8?
8 is the number of electrons in
Okay.
bonding orbitals.
Top versus 2p minus.
Yeah, so let's,
Okay, I got it.
so it's this one is bonding, and this one is bonding, and these 2 are bonding. So it's the one in the green minus the ones not in the green with the stars. And it's really messy, I'm sorry. Other questions? So now let's go back to our example there and see if I can do it a little neater. So draw the bond order for N2 plus ion. Okay, so nitrogen. So nitrogen, maybe I'll space this out a little better this time. Nitrogen's valence electrons are in the second energy level, second principal quantum level. We've got 2 nitrogen atoms. How many valence electrons does nitrogen have? 5. So we're going to fill these in. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. But we're not doing N2. We're doing N2 plus. It means one of these atoms is short an electron. So I'm going to erase that last electron I put in and put a plus on this guy. Because when you put these 2 together, you'll get N2 plus. Now we have to combine these into the molecular orbitals. So the S will make a sigma to S and a sigma star to S. And the P, there's going to be a sigma 2p and a pi 2p and then a pi star 2p and a sigma star 2p. So 3 orbitals from each side, and we end up with 6 orbitals in the middle there.
Isn't this the one that flips?
Very good, yes it is. This is the one that flips. Be careful now. So in that situation, then it was these two that flipped, right? Let me double check that. It's the bottom two that switch, the pi 2p and the sigma 2p. So we're going to take these guys out and move them around. That's the order we expect, but it's not what these guys do. They have a reason, but
And that happens only for, oh, be careful.
be careful now.
It's too late.
I know. Okay. That little sentence, be careful now, that really does help. Boron, carbon, nitrogen, gotta be weird. Fine. Okay, so we've got a total of 9 electrons, right? 5 from the one nitrogen, 4 from the other. And so we're going to put them in, starting at the bottom and going up. 1, 2, 3, 4, 5, 6, 7, 8, 9. So what's the bond order? How many electrons in bonding orbitals do we have? 7, right? 7 in bonding orbitals. How many in antibonding? 2. Divided by 2. So that's 5 halves, or 2.5, right? Do we expect this to be a stronger bond or a weaker bond than in nitrogen, N2? Well, what's the bond order for N2? Well, we could go back and look at the table in the book, or we could make this into N2, because the difference is an electron, right? And so for N2, it would be 8 minus 2 over 2, which is 3. That's for N2. This is N2 plus. So for N2 plus, the bond order is 2.5. Does that mean the bond is stronger or weaker? It's weaker than a nitrogen, N2. I added this red one so that we could look and see what the bond order for N2 was.
Wait, where did you get the 8 and 2?
Where did I get the 8 and the 2? Actually, let's do it this way. So here's bonding, bonding, bonding. Okay, that's these guys. The bonding orbitals. Oh, that's how we do that. And then these are anti-bonding orbitals. Does that help?
And then the red one was added in there because it's N plus.
The red one, so in the green, we were doing N2 plus, which was what was asked for. But then they wanted us to compare that to the N2 molecule. We need to know the bond order. And so I put the red one in there so that we could look at N2 and see the bond order for N2. But the red one is not part of the diagram for N2 plus. So is the N2 plus ion diamagnetic or paramagnetic? The plus is paramagnetic because that guy's not in there for the N2 plus. So it would be paramagnetic. It's got an unpaired electron. N2 is diamagnetic. It has only paired electrons. Interesting in sort of a complicated, weird sort of a way. You guys want to take a break? Or you want to keep going? Keep going. You're kind of on a roll, so. Okay, so second period, heteronuclear diatomic molecules. Let's look at nitrogen monoxide. Oxygen is more electronegative than nitrogen. So its atomic orbitals are lower in energy compared to the nitrogen. The atomic orbitals for oxygen are lower. Yeah. You have to look, you see this diagram and it pops up at you and you're like, you have to kind of look at it for a while. It's like, what on earth, what is that? Orientate yourself. So when the atomic orbitals are different in energy, what happens? Well, the lower energy atomic orbitals can contribute more to the bonding orbitals, and the higher energy ones are going to contribute more to the anti-bonding. So when we look at this, we have 2s and 2s. They're going to combine and form these molecular orbitals, O2s, sigma 2s, and sigma star 2s. But this anti-bonding is going to be closer in energy to the higher energy atomic orbital, and the bonding one is going to be closer to the lower energy atomic orbital. And here we've got the p's combining, and we're going with just the expected order, because you could say, well, but nitrogen was in that group that did the crazy order. That's only when it's nitrogen with itself. Here it's with oxygen. So we're going to get this sigma 2p, pi 2p, pi 2p star, sigma 2p star. But these anti-bonding ones are closer to the higher, and the bonding ones are closer to the lower energy ones. So nitrogen has 2, 3, 4, 5 valence electrons. Oxygen has 6. So we've got 6 plus 5, 11 electrons. And we put them in 2, 4, 6, 8, 10, 11. What's the bond order for that? How many electrons in the bonding orbitals? 8. And how many in the anti-bonding? 3. So this is anti-bonding, and this one's anti-bonding. And the others are bonding. So 8 minus 3 and divide by 2, and that's 2.5. Is this paramagnetic or diamagnetic? Paramagnetic. It's got an unpaired electron. It's got a bond order of 2.5, so we expect that it does exist and should be stable. So here we're looking at hydrogen and fluorine. Fluorine is the most electronegative element. So fluorine has its 2p orbitals here, and here's hydrogen with its 1s orbital. And so what happens is, because it's so electronegative, all of its valence electron orbitals, all of its valence orbitals are lower in energy than hydrogen's 1. We haven't talked about the relative energies of the atomic orbitals of different atoms before, different elements. And they're not all the same. They're different for different elements. Well, here we're combining an atom that only has an s orbital with an atom that has s and p orbitals. What appears to be missing over there? The 2s, right? Because fluorine has a 2s that's full. They didn't put it on there because it turns out it doesn't combine with the molecular with hydrogens to make a molecular orbital. So what happens is one of the p orbitals of fluorine combines with hydrogen's s orbital, and so we get a sigma and a sigma star, and then these are the two non-combining orbitals. They're not anti-bonding, they're non-bonding. They're just neutral. Basically, they're just the atomic orbitals with their lone pairs in them.
Oh, because hydrogen doesn't contribute to any other.
Yeah, hydrogen is only going to contribute its valence orbitals, and it only has the one valence orbital. It doesn't have any p orbitals to combine with the p orbitals from fluorine. And I don't expect this one to make much sense to you. It's like, oh, that's a little random. Why do we have to go into that? Didn't we just do that? Yeah, we did. Now this is the sort of thing that if it's asking you to find a bond order or draw orbital diagrams, like here with nitrogen and oxygen, they each have their own ordering, and so this is telling us use the energy ordering of O2. And that's what was done. Instead of drawing this out, we'll just go back and look at the one that was done. I need to change that slide. Actually, we already answered all those questions, didn't we? It's paramagnetic, and the bond order was 2.5. Oh, so we'll just skip that example. What about polyatomic molecules? Well, if we look at ozone, ozone's just barely polyatomic, right? It's got 3 atoms instead of 2. And we looked at resonance, right? And the Lewis theory is real limited in explaining how these bonds are. You know, we talked about it's not really flipping back and forth, but these are hybrids in between, and it's like each of them is 1.5. We know experimentally that the 2 bonds in ozone, are equivalent. Valence bond theory doesn't explain this either, because this is what you get from valence bond theory. You get this double bond, a sigma and pi bond between 2 oxygens, and a sigma bond between the other. And these bonds are not the same. So what happens in molecular orbital theory? Well, in molecular orbital theory, the pi molecular orbitals form from a combination of 3 2p orbitals, one from each atom, and they get delocalized over the entire molecule. And so the molecular orbital theory explains how these bonds can be the same. A p orbital from this oxygen and a p orbital from that oxygen and a p orbital from this oxygen all combine to make this weird shape. And the electrons in these orbitals are delocalized. They're shared over the entire molecule. Another molecule that Lewis and valence bond theory have trouble with is benzene. Benzene is a 6-carbon ring, and it's got 6 hydrogens, each of them attached to one of these carbons. And when we do Lewis structure, we find we end up with alternating double and single bonds on this carbon ring. And in this way, each carbon atom has an octet of electrons. But then we have this resonance structure where the double bonds are in the other places. And so we're saying, well, it's between these two. Well, molecular orbital theory helps us to understand how benzene is. We're going to get these pi molecular orbitals from 6 2p orbitals that are delocalized over the entire molecule. So each of these carbon atoms has one p orbital that's contributing to this pi bonding. And so it gets delocalized. And this is consistent with our observations of the properties of benzene. It's highly symmetrical, and it has 6 identical carbon-carbon bonds. It is not alternating double and single bonds. That's the end. That's as far as we're going.